Welcome Calculus 3 fans. In this video we're going to be discussing an introduction to the material from Chapter 11. Chapter 11 contains two main ideas, and those two main ideas are sequences and series. So start off with a discussion of sequences. A sequence is a list of numbers. Here's a perfectly good example of a sequence. The list of numbers 1/2, 2/3, 3/4, 4/5, 5/6, and so on. Now you can see two things about this sequence. First, it's a list of numbers that's defined on the positive integers. Second, it's an infinitely long list, and those are two factors that will usually be true for our sequences too. Now, one of the things we're going to be interested in is coming up with a formula that describes the nth term of the sequence. And that nth term is pretty quick to see here. The nth term of the sequence can be described as a sub n equals n over n plus 1. Now, a second thing we'll be interested in trying to understand is what happens to our sequence as n gets large. Now, a good way to investigate that initially is to think about a graph of the sequence. So here I've plotted that same sequence, n over n plus 1, for the first 20 integers, 1 through 20. So you can see 1/2, 2/3, 3/4, 4/5, and so on and so forth. And it appears graphically, at least, that this sequence approaches 1. That turns out to be true, and we'll go back to our old friend from Calculus 1, the limit, in order to make that clear analytically. This idea of what happens to a sequence as n goes to infinity, and in particular, whether it closes in on a number, is called convergence. So in general, we'll be interested in determining whether a given sequence converges. Now, the second thing we'll be talking about in this section, which is similar but a little bit different from a sequence, is a series. So a series is a sum of numbers. To motivate a series, which, similar to a sequence, is an infinitely large sum of numbers that is defined on positive integers, I'll go ahead and give the following geometric example. So let us consider a square with side length 1. Now, I think you'll agree, of course, that this square with side length 1 has area of 1 square unit. Now, something we can do for fun is take out our magical mathematical scissors and cut this square in half. So if we do that, of course, the area of the rectangle at the bottom is 1/2. And we can do that again, and the area of the square that's left is 1/4. And we can keep doing that over and over and over again, at least in theory, forever. So here you can see we've divided the square into a whole bunch of smaller squares and rectangles. And if we think about adding up the areas of all of those smaller squares and rectangles, we get a series, an infinitely large sum. The series is 1/2 plus 1/4 plus 1/8 and so on and so forth forever. And you can imagine, at least geometrically, that that area had better be 1. So here's a perfectly good example, again, of a series that closes in on a particular number, and we'll come up with a way to justify this rigorously also, this idea that a sum of an infinite number of numbers can be equal to a single number. And again, that idea of closing in on a number is this idea of whether a series converges. Okay, so sequences and series. A series is a sum of numbers. A sequence is a list of numbers. In both cases, we'll be interested in determining whether they converge. All right, thanks for your attention, and we'll see you next time.